Imagine a mechanical automaton programmed to build a complex, towering structure. It works perfectly, placing every beam with precision. But the moment it finishes for the day, it instantly dismantles the entire tower, guaranteeing tomorrow it has to start over from the first bolt. When software developers use AI agents today, they are working with that exact same automaton. A developer might spend Tuesday guiding an agent through a complex debugging session. The agent reads the worker code, diagnoses a race condition, and implements a fix by adding a precise 200 millisecond initialization delay. On Wednesday, the developer asks that same agent to add a new feature to the exact same file. Because large language models are stateless, the agent opens with a completely blank context window. It reads the code, sees the 200 millisecond delay, flags it as an arbitrary error, and prepares to delete the very fix it wrote yesterday. To prevent this, developers must constantly remind the agent of past architectural decisions, complex bug fixes, and learned conventions. As a software project matures and accumulates history, the computational cost of the agent rediscovering and processing this context grows without bound. Without persistent memory, every session starts at zero. Eventually, the computational cost of establishing baseline context outweighs the value of the agent's actual execution work. Traditional Retrieval-Augmented Generation, or RAG, a common method of giving an AI access to external knowledge bases, fails to solve this problem. RAG treats documents as largely static files and inherently lacks the chronological causality needed to understand the sequence of a project's development. Model fine-tuning is also an inadequate alternative. Updating an LLM's core WITs is far too computationally expensive and slow to accommodate the daily, incremental knowledge updates required for an active software project. Static system prompts, like dedicated rule files in a codebase, require constant manual curation from the human developer. Furthermore, they permanently consume valuable space within the agent's strict context window limits. A continuous 150-day production deployment of a system called ClaudeMem demonstrates a different approach: progressive impression. This is a 5-stage architecture designed to give agents experiential temporal memory without modifying the underlying model. This architecture captures the agent's actual tool use events in real time. By compressing these actions, 150 days of project history can be securely injected into a mere 2,500 tokens at the start of a session. True agent memory requires recording what the agent actually experienced and exactly when it happened, rather than simply retrieving what a static document says. The first stage of the progressive compression pipeline is capture. The system uses an asynchronous background hook to intercept the primary agent's tool invocations, such as file reads, code modifications, and shell commands. Because this capture mechanism operates asynchronously, it records what the agent does in real time, while ensuring zero latency impact on the user's immediate workflow. This creates an immediate architectural bottleneck. Raw terminal outputs and the contents of full file reads are massive. They are far too large to store efficiently, and impossible to inject directly into a persistent context window. The second stage of the pipeline solves this by routing the massive raw output into a secondary, cheaper model known as the Observer LLM. The Observer LLM applies heavily lossy compression. It intentionally discards the raw code and extracts only the task-relevant data, structuring it into an XML observation containing a short title, categorical tags, and a factual narrative summary. Delegating memory creation to a secondary model completely isolates the cognitive load of data compression from the primary agent, allowing it to remain focused entirely on its execution tasks. A large block of 3,775 discovery tokens, the compute to process one tool event, shrinks into a dense 343 token node, an 11:1 compression ratio. This node expands to reveal a schema: title, type, concepts, and a narrative bullet. Reading this is 11 times cheaper. The Observer LLM discards the raw file code entirely, preserving only its own judgment of what was logically relevant to the specific task the primary agent was trying to accomplish. Intentional information loss is a necessary feature, not a bug, for scaling long-term agent memory within fixed, finite context windows. The third stage of the pipeline takes these newly compressed observations and stores them in a persistent database. Standard vector databases, storage systems that map information as mathematical coordinates to find similar concepts, have a critical limitation when applied to agent memory tasks. While vector search perfectly maps semantic relevance between two related ideas, the retrieval mechanism has absolutely zero concept of time or chronological sequence. Understanding causality requires strict temporal ordering. An agent cannot understand why a specific bug fix was implemented unless it knows that the fix occurred immediately after a specific failed test. This dual database architecture splits incoming data into two storage containers, a clustered network graph for semantic similarity and a linear chronological timeline. To process a query, it filters the network graph for topically relevant nodes, then extracts and plots them on the timeline, ordering semantic results chronologically. Experiential memory requires mapping semantic meaning directly to strict temporal sequence in order to maintain logical causality for the executing agent. The final stages of the architecture involve searching the dual databases and injecting the contextual memory directly into a brand new agent session. During development, the engineering team tested a just-in-time, or JIT, context filtering system. They used an LLM to dynamically evaluate and select only the most relevant memories for each specific new user prompt. This highly sophisticated AI-driven context selection system was completely abandoned after just 4 hours in production. The computational latency of running a smart AI query to select observations vastly outweighed its theoretical benefits. The smart approach was simply too slow. This failure revealed a clear engineering principle for continuous software development. Chronological recency is actually the strongest prior for relevance. The system pivoted to injecting a simple, hard-coded timeline at the start of every session. As this diagram shows, it injects the 50 most recent observations as a dense, compact list of single-line entries, each featuring a timestamp, a categorical icon, and a short title. Simple temporal injection outperforms complex AI-driven selection because large language models are already highly efficient at filtering out and ignoring irrelevant information at read time. This architecture presents a central paradox. How can a mere 2,500 tokens of heavily compressed summaries successfully proxy for 189,000 tokens of raw analytical compute? This image illustrates the semantic priming hypothesis. This theory posits that the injected timeline acts as an index. Instead of supplying raw data, the short text string triggers the LLM's pre-trained knowledge, illuminating a massive, complex neural network of existing information. If a compressed timeline mentions a recognized pattern, like an express router, a standard web component, the LLM already understands the underlying mechanics from its pre-training. It only needs to know that the pattern exists in the current project. This priming effect converts deep, multi-file context discovery into an instant, highly efficient lookup operation for the agent. The compressed timeline serves as a map, explicitly telling the agent what it already knows about the current project's state. This chart contrasts the two memory paradigms. The exponential curve shows the cost of unbounded rediscovery, where the context required to understand a project grows endlessly as changes accumulate. The flat horizontal line shows bounded injection, where the computational cost of establishing context remains strictly capped at the initial injection depth. Solving memory bottlenecks shifts LLMs from disposable, single-session tools into long-running, asynchronous collaborators that retain the specific history of your work. 150 days of complex project history can be maintained securely and transparently entirely on a local machine without ever modifying the underlying model weights. The statelessness of LLM agents is not a permanent hardware limitation. It is nearly an engineering choice that can now be solved directly at the application layer.